In this video, we're going to take a few minutes to look through some sample problems. In each case, I highly recommend that you pause and try and work through the problems before looking at the solutions. So first, we have some problems relating to valence bond theory and hybridization. So here, we're going to consider the molecule NO2, which has the structure that's shown. The left-hand figure is showing the three-dimensional structure. The right-hand figure is showing the connectivity of the atoms. And so the types of questions you could be asked about this are things like how many electron groups are around the nitrogen atom? What is the hybridization of the orbitals around the nitrogen atom? How many atomic orbitals are used to form the hybrid orbitals? And what unhybridized orbitals are also on the nitrogen atom? So hopefully you've paused and taken a minute to think about this on your own, but now let's go ahead and talk about it. So on the nitrogen atom, we have one lone pair, we have one double bond, and we have one single bond. That gives us a total of 3 electron groups. So we would count this as 2 bonds and 1 lone pair. This means that we're going to need 3 hybrid orbitals for our nitrogen atom. If we need 3 hybrid orbitals, we can form those using 1 s orbital plus 2 of the p orbitals. And so this would give us a hybridization of sp2. So this also answers the next part of the question where we need 3 atomic orbitals form 3 hybrid orbitals. In the sp2 hybridization scheme, we've used up 2 of the p orbitals. So there's going to be 1 leftover p orbital left on the nitrogen atom, and that's going to be in the 2p level. So we have 1 2p orbital left on the nitrogen atom. And this leftover p orbital is actually what's going to participate in bonding with another p orbital on the oxygen atom to form the double bond part of this structure. Here's another set of questions on valence bond theory and hybridization. Take a minute and pause the video to think about these questions. So hopefully you've had a minute to think about this. So let's go ahead and talk about these questions. Here, a molecule has sp hybridization. How many electron groups does that correspond to? So in sp hybridization, we're combining an s orbital and a p orbital. And so this is going to correspond to 2 electron groups. There's 2 sp orbitals, and that basically is going to connect to 2 different electron groups. Those would happen basically when you have a linear molecule. An example could be something like CO2, where we have a carbon in the middle connected to 2 other electron groups. If we have sp hybridization, that gives us 2 hybrid orbitals, and so we can form 2 sigma bonds. In an sp hybridized atom, we also have 2 leftover p orbitals. So every atom always has an s orbital and 3 p orbitals. And so if we've combined 2 of those to make our hybrid orbitals, we have 2 leftover p orbitals. So we could form a maximum of 2 pi bonds. And this last question's a little bit different. It asks us to think about the energy of a triple bond and think about why that is lower than 3 times the energy of a single bond. So a triple bond is actually formed from 1 sigma bond and 2 pi bonds. Sigma bonds are going to be lower in energy or more stable than pi bonds because they're formed by orbitals along the bonding axis that overlap, and so they have better overlap. If you have multiple bonds, they always have one part of the bond that's a sigma, and then the other parts are pi bonds. And so with a triple bond, we would have 1 sigma bond and 2 pi bonds. And so the reason that it's not just 3 times the energy of a single bond is that we have 2 of those bonds that are higher energy and easier to break. For a last question about hybridization, let's think about SF6. So SF6 is a molecule that has 6 equal bonds. Explain how you can have a molecule with 6 bonds that are equal using the hybridization model for the sulfur atom. So again, pause the video, take a minute, and think about how this is going to work. And assuming you've done that, let's proceed to discuss the answer. In order to get 6 equal bonds, we need to have 6 equal orbitals. And so that happens when we combine an s orbital with 3 p orbitals. That's all of the p we have. And so then we have to move into the d orbitals. So that gives us 6 sp3d2 hybridized orbitals. We also have some leftover unhybridized orbitals. For sulfur, we have 6 valence electrons. And so we can fill those in the s and the p states. But when we hybridize them, these energy levels are now all at the same energy, and so we would spread them out into the 6 separate d orbitals. That now gives us 6 electrons that can bind with 6 fluorine atoms, and these hybrid orbitals are what form equal bonds. For this next question, we're going to move on to thinking about molecular orbital theory. So using the given molecular orbital diagram for N2, fill in the correct number of electrons in the molecular orbitals, and then think about what the bond order would be, and whether N2 plus would have a longer or shorter bond than N2. So nitrogen has 5 valence electrons, and so each atom is going to have 5 valence electrons, so I can fill those in. That means I have a total of 10 electrons that I need to put into the molecular orbitals. And so I start filling bottom to top. In general, if you ever have degenerate orbitals, you want to fill them in one at a time before adding in the pairs. And then we add in 2 more into the sigma level. So this gives me a total of 8 bonding electrons and 2 antibonding electrons, which means I can calculate the bond order as 8 minus 2 divided by 2, which is equal to 3. So we would say that N2 has a triple bond. I could also have calculated this ignoring the sigma orbitals because they're both bonding and the antibonding are equally filled. In that case, I would have had 6 minus 0 divided by 2, which is also 3. So either way, I conclude that nitrogen has a triple bond. For N2 plus, we need to consider removing one of these electrons. And so I would have a total of 9 electrons. What this means is that I can calculate the bond order for N2 plus, which would have 7 bonding electrons, 2 antibonding electrons, and I divided that by 2, so I get a bond order of 2.5. This means that N2 plus is going to have a smaller bond order and therefore a weaker bond. And the weaker bond is also going to correspond to a longer bond. So N2 plus would have a longer bond because it's weaker. N2 minus, by the way, would also have a weaker bond, but for a different reason. In N2 minus, we would be adding an electron to a pi star orbital. So removing an electron from a bonding orbital or adding an electron to an antibonding orbital both result in a weaker bond. For this last problem, now you get to draw your own molecular orbital diagram for lithium fluoride. And we give you a little bit of information about the energy levels. So the 2s orbital on lithium is going to be higher energy than the 2p orbitals on fluorine. So if you've taken a minute to think about this, then let's go ahead and look at the solution. So if we're thinking about our energy increasing as we go up, our lithium 2s orbital is going to be here, which means the 2p orbitals would be even higher. The fluorine atom, we're going to have a 2s orbital that's somewhere lower, and 2p orbitals that are higher, but still somewhere below the lithium. So lithium has 1 valence electron, which we would put in the s orbital. Fluorine has 7. And so in this case, what we're actually going to consider is the interaction of the 2s orbital with the 2p orbitals because of the energy differences. So we would have a bonding molecular orbital that's going to give us a slightly lower energy there, and an anti-bonding molecular orbital that gives us a higher energy. And we can put in the lines to sort of guide where this is coming from. The leftover orbitals on the fluorine would be considered non-bonding, and so they would just come directly over. And now when I go ahead and think about filling in my electrons, I have a total of 8. And so from my molecular orbital diagram, I would go ahead and calculate the bond order as being 2 bonding electrons, 0 antibonding electrons divided by 2. And so we would say that this forms a single bond. Notice that we're not including the non-bonding electrons in any way when calculating the bond. The next question asks if these electrons are shared equally. As I've drawn it, we know that the electrons on fluorine are lower in energy. It's the more electronegative element. And so in the bonding orbital, the electrons are going to be closer to the fluorine. They're going to be in an orbital that's essentially a 2p fluorine atom. And so that explains why they're not shared equally. It's basically just because fluorine is more electronegative, and therefore the bonding orbital looks more like a fluorine orbital. In the last question, we're asked about LiF minus and LiF2 minus. So LiF minus would result from adding 1 more electron, and the only place to add another electron is to this antibonding orbital. So LiF minus would have a bond order of 1/2. LiF2 minus would result in adding a second electron here. And so we would have 2 bonding, 2 antibonding electrons. And so when we subtract that, we get a bond order of 0. And so from this, we would predict that yes, this can exist. It'll have a weak bond, but LiF2 minus would not have a bond because it has a bond order of 0. So hopefully this helped you understand a little bit more about the types of problems you could be expected to do with these theories of bonding, and make sure to do some more practice on your own in order to make sure you really understand the topic.